Welcome to the ipXchange community and members and viewers. We hear lots of companies claiming that they can enable OEMs to perform edge AI, all sorts of applications, speech, voice, video, vibration, analysis, whatever, with high resolution, high performance, and at very low power. Today, we're going to investigate another one of those with a company from Waterloo in Canada, Applied Brain Research. So I'm delighted to be joined by Kevin and Chris from Applied Brain Research, Kevin CEO and Chris the CTO, and we're going to talk about Applied Brain Research's TSP product and that family of processors and their claims for high edge AI performance and low power. Kevin, Chris, I'm very glad you can join us.
Thanks for having us, Tim.
Great to be here.
Great, very good. So let's start with establishing who it is who's really going to be excited by your product and what you can do. So it is kind of a broad umbrella term. Are there specific kinds of applications or end product types for which you're really most suited and where your claims of performance and low power operation really do come to the fore?
Yes, definitely. So the general class of technology that we have is for time series processing. That's what our TSP1 stands for. And where we've seen people most excited about our technology is in applications like voice interfaces, where the responsiveness of the AI is super critical for the application. And as we've looked at the broad spectrum of devices that are integrating things like speech to text, text to speech, natural language understanding, we found a variety of these that are super sensitive to that responsiveness in order to have realistic and convincing interfaces for people to use. And as part of that, seeing the challenges that people have had when they try and use cloud-based solutions or even to take embedded solutions that are running on powerful edge AI processors, the challenges that are there in terms of responsiveness, the power consumption, the cost of these solutions, and even to see the end user concerns about sharing their voice data with a cloud processor, the data privacy issues that come up as part of that concern. So what we found is the most excitement from customers who find out that they can actually integrate this directly into their product, to have a voice interface directly integrated into the product that runs at really low power and is super affordable and easy to integrate.
And can you give us some use case examples of where this real responsiveness of the speech processing function is really critical?
Sure. Things like speech transcription for live video capture, for example, that happens in VR glasses, voice transcription for helping hearing impaired visualize speech that's happening around them. It might be applications like voice control, where you want to have real-time local control over a device with voice commands that go beyond the simple keywords or key phrases, but actually understand what the person is saying and can take action based upon that. Those are some examples. Other ones are where you want text to speech generated in the edge device without it having to be connected to a cloud in order to be able to deliver realistic human sounding speech for people from text that's embedded in the device.
Yeah. So what you're able to deliver is in these applications is latency that's so minimal that the user doesn't really experience any kind of delay at all?
That's correct. With cloud-based solutions, it can be very frustrating to wait 3 seconds or more to know if your device actually even heard what you said. So being able to deliver that under 2 seconds, in some cases, hundreds of milliseconds, depending on what the end device needs, it's a far different experience of having that ultra responsive type voice control.
Is this natural language operation, or is it a kind of a subset of a total language? Is it kind of keywords or a certain sort of restricted vocabulary?
The beautiful thing about our solution, it can be any of all those things. So for example, we can combine trigger words that might control greater functionality in the chip, and that allows us to operate at even lower power in those devices. But typically when we talk about our speech technology, it's using full vocabulary. So we want to enable things that are not limited to a small set of keywords or key phrases, just because people tend to have a hard time remembering those. Even interacting with our smart speaker devices, can't tell you how many times like, oh, what did I call that function? Or what does it need me to say? That can be extremely frustrating for people. And so we want to make these interactions with humans and between humans and devices much more natural.
And you talked about speech as being, if you like, the flagship application for your product at the moment. But you talked about actually applicability to time series processing. Can you describe what you mean by time series processing, and then sort of what other kind of applications then does this suit apart from speech?
Well, we have one of the world-renowned experts in time series processing here with the AVR CTO, so I'll hand it over to Chris for that.
Sure. So time series processing is basically whenever the order of the data matters for the inference that you're trying to make, then we would call that a time series. So this pops up kind of everywhere. Interestingly, historically, not in deep learning so much. So people started typically with images where there's no particular ordering. But when you think about the stock market or, of course, language, the order of the words matter. Same with voice recognition. And the other applications we've been looking at are around biosignals. So you're trying to do any kind of monitoring of heartbeats or changes in oxygen levels in the blood and so on. Those would all count.
Yeah, excellent. Okay. So your kind of claim to fame, the reason why you would want our ipXchange viewers to really take an interest in the TSP1 and in applied brain research is because of this kind of really super fast performance of ultra low latency, but also operating at low power. Do tell us what you mean by low power in this context, but I wonder if you can also explain, because ipXchange viewers will be very, very familiar with microcontroller offerings, for instance, and we're talking about edge applications here. Most of them are going to be basing their designs on a microcontroller, and microcontroller manufacturers left, right, and center are shouting loud about their ability to do AI at the edge, no cloud connection needed, and on battery power. They're developing products that combine the traditional CPU with a neural processing unit with an NPU to enable them to do really accelerated AI operations. Those microcontroller manufacturers, names that we're all very familiar with, are claiming that they're offering real-world proper AI performance and at kind of battery kind of power. They're claiming they can do that. Is it true? And to what extent are you kind of moving beyond them in terms of either performance or low power consumption or both?
Sure. So what we've seen for things like speech recognition, natural language understanding in embedded devices, there are some very powerful processors out there for edge applications that doing that. They're available from ST, NXP, Qualcomm, Samsung, Rockchip, MediaTek, even NVIDIA, right? The list goes on and on. One thing that we've seen that's very, and they're very capable processors, no doubt. I mean, these are systems capable of running Linux and very, very powerful embedded neural network capabilities as well. But there's two things that we've seen when some of our applications, they have to run all the time. So if we want a device that's capable of producing, again, speech visualization for certain applications, it has to run for several, not just minute sessions, but people are going to use these for hours at a time. And the challenges involved in real-time, low latency time series processing running on these processors is that it consumes massive amounts of memory bandwidth to do. And when we talk about memory bandwidth, we're talking about power. So while these processors are very powerful and capable, they consume an inordinate amount of power to run these applications. So anywhere from 3 to 12 watts of power are consumed. So for devices like, and we're talking about now more capable devices like robots and some of the current augmented reality glasses and those sort of things, the use of power in both of these, they have very different battery profiles in terms of how many milliwatt or kilowatt hours that they have in there. But one thing that's common is the amount of power that they have that can be dedicated to speech functions, for example, is extremely low. So, for the companies that we have talked to, there's not, they want to reduce the amount of power that goes into these functions. And so even though these processors can do it, it's a poor power choice for those functions, especially when it might be one of the most primary functions of the device we're talking about. You don't want to be burning 3 watts of power if you can be burning 30 milliwatts of power using our product,
Okay.
right?
Okay. So is the problem for these, just to interrupt, is the problem for these, the kind of microcontrollers, microprocessors that you've been describing, that they are, maybe the problem, it could be both an advantage and a disadvantage, that they're kind of general purpose devices in a sense, that they're equally kind of well or poorly adapted to video, to voice, to vibration, to other kinds of AI application, whereas yours is actually specifically dedicated towards, as Chris was describing, the time series kind of data applications. So if time series is what your application requires, you're going to be better suited than something that's a more general purpose kind of device. Is that a kind of a correct way to characterize it?
Absolutely. And we should, for the time series processing domain, there are different classes of time series processing. So some might be things like heartbeat extraction or monitoring cardiac events and these types of things, which have to run all the time, and typically in wearables that are monitoring people remotely. And so super sensitive to that. So those kind of applications are not going to choose these really high powered general purpose computing platforms for them. And so there it's about elevating the capabilities of the time series processing that's possible in those products. And for the other applications, certainly when you do specialized computing, do specialized solutions for this, we bring the ability to have a tailored time series processing platform that manages the memory bandwidth and the computing in such a way that it's super optimal and minimizes the expenditure of any power for that processing. So it's a great reduction that you would otherwise spend on these general purpose platforms.
Tailored to a specific customer's application?
Yeah, so the nice thing is the customer can take the AI networks, tailor them to their specific applications. So for example, in voice, you might want to select which languages you want to support. You might want to have different sort of microphone options integrated into your device and play with the sample rates and make it exactly what a customer is going to want. But at the core of it, the neural networks and the processing of it don't have to change. So, it's that breadth of customization that we allow customers to do.
So that's interesting, because we're used to dealing with a world of microcontroller manufacturers where the chip is the chip. It has a bunch of features and capabilities, and the customer, the OEM, does what it wants to do with that chip within the constraints of that chip applies. You're describing something that more customizable or configurable. So can you explain to us, we've talked about the TSP1 as being the processor device that you produce, but it sounds like your product offering is actually about a little bit more than just a chip.
It's way more than a chip. Yeah.
Okay. I think you better explain.
Sure. Well, I'll explain, maybe from the customer side, how we've seen customer desires, but Chris is better to dive into the technology stack behind it. There are some customers that just want a solution. It's like, I want to add speech recognition to my device. How do I do that easily? I'm not a machine learning expert. I don't know how to configure a neural network. I just want to say, I want it to work this way. I want my product schematic to be this, I want to push a few buttons and get my solution. And then there's the realm of the AI experts. Everybody's building their own AI team. And even for those that are not experts, there are some that just have a huge interest and desire to build networks and to work in this space. So for that, there's a lot behind that. And again, Chris is the expert here, so I will step back.
Sure. Yeah. Happy to jump in. I think one thing that is critical to mention is that we see as a key differentiator an algorithm that we've developed. So I'm a professor here at the University of Waterloo, and my lab focuses on doing research on how the brain works. And we're known for having built the world's largest functional brain model. And in some of this research, we essentially discovered an algorithm that's used by a part of the brain called the hippocampus for encoding temporal data, time series data. And really what the chip is an implementation that supports that algorithm natively. As you said, most chip companies are, here's a chip, it's got a bunch of constraints, now do whatever you want. We actually think that to get the most efficient running AI, you want to have your hardware and your software or algorithm essentially being co-optimized. So in order to do that, you have to have a lot of confidence in your algorithm, right? You don't want to pick the wrong one. As everyone knows, these things change constantly. Conveniently for the algorithm that we discovered, we're actually able to prove that it's optimal for time series compression. So it's very unusual to be able to prove anything about these neural networks. They're infamously black boxes that we don't know how they work. But in this particular instance, we actually have mathematical proofs of the ability to represent time series data extremely efficiently, in particular in a streaming context. So this is why edge applications seem like the important ones. So with that in hand, and we've got lots of data and papers and everything to show that these algorithm outperforms transformers and LSTMs and GRUs, all the ways that people typically do time series processing. So with that data in hand, we set about building this piece of hardware to be extremely good at running that particular algorithm. So in some ways, this is a bit of an additional constraint. But in other ways, given the optimality proofs and all the evidence we have about how good it is at time series processing, we think it was the right choice for customers who want the best low power solution. The advantages are things like, we need half the memory to get the same performance as a transformer on NLP tasks, for instance. So what we did was try to address the customers who don't really want to know anything about the algorithm. They just want out of the box solutions. So we have a platform that they can go on. They can choose pre-built, pre-trained using our algorithm. We know it runs really well on the hardware. They can select those and kind of go from there. And then for the AI experts, if you dive into that platform, you have the ability to change all of what we like to call hyperparameters that govern exactly what that architecture looks like, the neural network architecture looks like, implementing this algorithm in a way that's going to best suit their particular application. And this means that we do support other types of neural networks. We do support transformers and we do support convolutional networks and all these things that people will be familiar with. But we know that a key value is having uniquely on our platform this algorithm, which is typically known now as a state-space neural network. And we're also quite confident in the IP that we have surrounding that. So we invented the state-space neural networks, and we have a lot of confidence that we're basically the only ones who can really put this on hardware in the way that we're doing right now. So hopefully that gives you a sense of our differentiation.
Yeah, I mean, and many sort of companies in the AI field will look to the brain as kind of, neural networks are looking to the brain as the model for how you can do this kind of mental processing. Can you sort of explain how your the space state neural network is that the correct term?
Yeah,
state space. There we are. So is that something that you could see one day replacing, superseding sort of the neural networks that we're familiar with? You mentioned convolutional neural networks, for instance. Is it likely to replace those, or is it somewhat sort of complementary to them for specific kind of applications like speech processing?
Yeah, it's a great question. So we have published work on, of course, this algorithm, and many other research groups have picked it up and gotten their own fantastic results. And there are other companies using these techniques as well, applying them to things like large language models because they have advantages over transformers and so on. So to your question, we do think there are central advantages to state-space networks. So things like more efficient use of parameters for getting the same level of accuracy, being much better at dealing with very long time windows when making an inference, being more efficient to train. So we have demonstrations of using 10 times less data to get the same performance as a transformer. But ultimately, when it comes to applications, you are often combining that kind of core advantage with familiar aspects from other types of networks. So attention networks from transformers, convolutional networks, as I mentioned before, and so on. So this is exactly why, in our development stack, we support all of those types of layers, and you can put them all together in the way that you find advantageous. But yeah, we do think, and many other people as well have shown, that there are key advantages that are alone sort of owned by state-space networks.
Yeah. So here you are. You're a professor at the university in Waterloo. You've got deep expertise in this field. Our poor old embedded developer who's maybe grown up in a world before AI and is used to traditional sort of embedded control methods of implementing designs. there's change after change after change with AI. And here you are, when we thought we'd kind of got our heads around good old neural networks. And so if I want to do kind of image processing or video processing or whatever, then I know I'm going to have to sort of turn to one of the established neural networks that exist. And here you are, Chris, you come along and say, oh, hang on, no, sorry, you can't use that one. I've got a whole new network for you. Is there a way for embedded developers to implement, what the technology that you've developed in an easy way? Does it require deep AI knowledge on the part of your customer?
No, definitely not. When we started developing our stack, we began with the idea that people would not be necessarily AI experts. At the same time, you need the flexibility for people who are AI experts. And if you're kind of mid-level between an expert and a novice user, then our stack will be very familiar to you. There will be layers, and in those layers, you can pick different parameters that determine how those layers work. You define a data set, you hit go, and it goes away, and it runs on a bunch of GPUs to optimize that network given that data set. So all of this kind of pipeline will be very familiar to people who have done any AI at all in the past. So yeah, we provide a web interface where you can easily interact with data sets, where you can, as I said, a predefined data set that predefined network that you can load up, and then you can add your data to that network and fine tune it. So this is something people will also be familiar with. So all of that standard pipeline for people who've done any integration of AI into microcontrollers will be extremely familiar.
Yeah, maybe it's worth saying that this is not, while the invention of state space networks happened with the LMU within AVR, the industry is already starting to recognize the power of state space networks. So you do have a state space offering from NVIDIA on their platform. Jensen Huang himself has said state space is probably the next generation after transformers that are important for people. There are many other projects in the open source space that are using state space networks. So this is a developing field. And as Chris said, the nice thing about it is, because of the mathematics behind the state space network, that it's really, you can prove that it's the best you can get. Like, you can't get better in terms of the core capabilities of the network. So from that perspective, I think there's a high incentive for people to become familiar with these and their capabilities. And one of the things that is a challenge and a huge opportunity for us is to make sure that we engage the community where it is and enable the deployment of these models in applications easily, but also provide a future path as the expertise builds to further derive additional benefit from our platform upon that expertise.
So while the provision of a state space network itself is not unique to you, so your uniqueness comes from the combination of that software plus the TSP1, the chip, the hardware that is optimized for that specific type of network.
Yeah, I think there's two things. So first of all, yes, our processor optimally manages the deployment of and the compute and how that's done in our processing fabric, and doing that without unnecessary data movement and additional bus activity. But another aspect of our technology that Chris alluded to, but we have patented this algorithm. While it's becoming a really exciting thing in the industry, the core patent for the algorithm, which is also very hard to get, and we've already had grants in North America, in Europe, and Asia. North America and Asia pending in Europe, is another differentiator for AVR as the originator of this technology.
Okay, so it's all very well for Jensen at NVIDIA to talk about it, but at the minute you've got a bit of a grip on that technology.
Yeah, we're happy to have his promotion.
Okay, very good. And let's just talk about kind of the wider implementation within a device design. So we're talking here, purely about the AI operation and the ability to do the kind of speech processing that we've been talking about. But how does the chip get sort of implemented into a system? Can you implement a single chip solution with your device? Does it have the kind of system control and processing kind of functions that you would typically expect in a microcontroller, for instance?
Yeah, that's a great question. When we looked at the fastest way for people to adopt this, and having been an embedded developer many years in my own past career, know that the challenge is when you introduce a new platform as an option for engineers, there's a challenge of figuring out how does it work different than the ones that I have, right? So our initial approach to this is to provide a coprocessor, not to provide an application processor. And in terms of how an embedded engineer would have the options for embedding us into their application, there's really two different ways of doing it. So we thought for an existing application that's already taking audio data into the application processor and either shipping it off to the cloud or putting it into its MPU, it can optimally just send it over an industry standard interface to our coprocessor and be able to ship us data and then receive output back.
So you're just offloading that audio part of the application and leaving the rest for the host processor to carry on doing.
That's correct. And then for applications where they might be looking at kind of a re-architecture of things and they don't want to be burning even having the front end processing of the audio on the application processor, that can be moved directly to the coprocessor. So we have the ability to directly connect to microphones or other types of sensors, again, over a variety of industry standard interfaces, and just be able to interrupt the host when there's inference ready for it to take.
Excellent. All right. Well, that's fascinating. I mean, so it's been really good to hear about the ability and the special advantages of your technology in these certain kinds of applications that you've been describing, the time series data sort of applications, the speech processing, the biosignal processing, able to do that with incredible low latency, really, really low power. And so is this technology available for deployment today? What's the status? You're a relatively young company. What's the status of the chip and the technology? How can people make use of it?
Yeah, so we have actually just within a few hours ago released our database to the production
So
house.
we're talking at the beginning of April in 2025.
That's right. So our schedule is with our lead strategic customers that we'll be providing them the first development kits for them using the production chip at the end of this year. In the meantime, we have FPGA development platforms for those early strategic customers that applications can be built on these chips, operate and behave for everything except for the power consumption exactly as our production chips will. So for the broader community, the production availability of development kits would be in 2026 in the early part of that.
Yeah, and you would, I guess, then hope to see some lead customers actually going into production also in 2026 then?
That's correct.
Yeah. Okay, very good. And where should people go to find out more and sort of begin their journey into the time series processor kind of universe?
Well, the first place to start is at appliedbrainresearch.com, which is our website. And, there's an ability for anyone interested in going deeper into the technology to log a request in there and tell us about their interests, whether they're generally interested in the technology or want to hear more about the TSP product, have that ability to then make that connection and follow up.
That's fantastic. And I'm sure many will. Thank you, Kevin. And thank you, Chris, for taking the time to talk to ipXchange.
Been a pleasure, Tim. Thank you for having us.
Thanks, Tim.